Math 1332, Chapter 10, Probability and Counting Techniques, Section 3, Combinations, Video 4, Combining Combinations with the Fundamental Counting Principle. Before we get started, I just want to address the background. The room in which I have my desk, where I normally make these videos, is currently loaded with lots of boxes and stuff because we are moving my daughter into a new apartment this weekend for college. And these things have been here for several weeks since she left her previous dorm, or excuse me, her previous apartment at a different college. So that's why I've been using a hidden background, because I've got a lot of stuff just stacked up in this room, waiting to be moved out. Well, loaded tomorrow and moved out the day after. But I just wanted to go ahead and use the actual background so you don't have all this jumping in and out and stuff. And I'll probably just use the actual background in the future, despite the fact that the room is currently full of boxes and stuff waiting to be packed and moved out. But I digress. It's time to start combining counting techniques to handle more complicated situations. And I should tell you, and I should have mentioned this earlier, that these techniques will be used to calculate probabilities of seemingly complicated situations in future sections. You might have been asking yourself, this chapter started out with probabilities, where did those go? Well, if you recall the definition or the way to calculate a theoretical probability, we have to know a number of outcomes in a sample space and a number of outcomes in an event. And sometimes it's impossible to list those outcomes, but we can count them using the techniques that we're currently building right now. So it will come full circle when we get to that section, which I believe is section 5 of this chapter. But let's take a look at an example of a problem that combines the formula for combinations and the fundamental counting principle. It won't seem it at first, but you'll see why it does. At one school, a student government consists of 7 women and 5 men. How many different committees can be chosen with 3 women and 2 men? All right, well, first off, whenever you're picking a committee, it's always going to be a combination. When you pick people to fill offices, that's a permutation because the order matters. But just selecting people to be on a committee, the order doesn't matter, so it will always be a combination. But this has 2 groups that we're selecting from. It might help to get an illustration. For example, let's say that we have 7 women, so I'll put 7 W's here if I can get this to draw. 1, 2, 3, 4, 5, 6, 7 women. And we have 5 men. We'll just put those in a different color. We'll put those in blue. No particular reason, just changing colors. And we want to get a committee by choosing 3 women and choosing 2 men. Now, we are assuming that these women are distinguishable from each other. In other words, they all have names and they're all individuals, and not it's just 7 W's and they all look exactly the same. So in other words, these are distinguishable, distinct objects that we're selecting from. I hate calling men and women objects, but generically speaking, in a combination problem, anything can be an object. So how does the combination thing fit into here? Well, it should be pretty evident that there are 7 women and we want to choose 3. And so it's a combination, and it will be 7C3. And the same thing for the men. There are 5 men and we want to choose 2, so that will end up being 5C2. But where does the fundamental counting principle come into play? Well, if you think about it, we have to make 2 decisions. We have to pick 3 women. We have to pick 2 men. So from a fundamental counting principle, which I'll abbreviate FCP, from a fundamental counting principle, we have 2 decisions to make. We have to pick 3 women, pick 3 W's, and we have to pick 2 M's. And if we know how many ways to do that, then we just multiply the 2 answers together. Well, how many ways can I choose 3 of the 7 women? And remember, the order doesn't matter. That would be 7C3. And how many ways can I pick 2 males? 2 men. That would be 5C2. So the fundamental counting principle says I got to multiply the number of ways I can make this decision, choose the women, and this decision, choose the men. But each of those decisions in its own right is a combination. Let me clear out the stuff on the bottom and then we'll figure out what this equals. All right. So we need to calculate 7C3 for the number of ways we can choose 3 of the 7 women, 5C2 for the number of ways we can choose 2 of the men, and then multiply the 2 answers according to the fundamental counting principle. Now it's just straightforward. For 7C3, the first number goes on top of the factorial, the second number goes on bottom, and so does the difference. 7 minus 3 is 4. Times, for 5C2, we put the first number on top of the factorial, so 5. The second on the bottom, so 2. And the difference, 5 minus 2 is 3. Now, this is a mess of factorials, but guess what? We can clean them up efficiently. Let's start with the 7 factorial on top. The larger factorial on the bottom is 4, which means if I write out all the factorials, 7, 6, 5, 4, 3, 2, 1, 4, 3, 2, 1, the 4, 3, 2, 1s cancel on the bottom. In other words, when I start writing out the 7 factorial, I can stop right before I get to 4 because I know everything from 4 down will cancel with the 4 factorial. But the 3 factorial is still lurking around. And we could do the same thing with the 5 factorial. And the larger of the 2 on the bottom. The 5 factorial goes 5, 4, 3, 2, 1. The 3 factorial goes 3, 2, 1. The 3, 2, 1s cancel. So if I start writing out the 5 factorial, I can stop right before I get to 3 because everything after that, 3, 2, 1 would cancel with the 3 factorial, but I still have the 2 factorial on the bottom, 2 times 1. And we could get out a calculator or we could do some massive cancellation. I will do that. In the first fraction, there's an easy way to do it because this 3 times that 2 together makes a 6, which takes out the 6. And on the other fraction, this 2 goes into that 4 2 times. Let's see what's left. And the denominator is just 1, so we're okay there. But in the numerator, there's a 7 left, a 5 left, another 5 left, and a 2 left. So really all I have to do is 7 times 5 times 5 times 2. Well, going right to left, I know 2 times 5 is 10. Actually, let's look at it this way. You always want to look at things from multiple perspectives. This is equal to 35. The one on the bottom doesn't matter. 7 times 5 is 35. This is equal to 10. 5 times 2 is 10. The one on the bottom doesn't matter. I have 35 times 10, which is 350. There are 350 ways to make this committee. Again, it was the fundamental counting principle because we essentially had two decisions to make. How do we pick the women? How do we pick the men? But for each of those, the number of ways to do it was a combination. Let's take a look at one more, and this one's going to be a little bit more complicated, but I bet we can figure it out. A resort manager is choosing a committee of 4 people to discuss employment issues. He'll choose from 8 housekeepers, 3 desk clerks, and 5 maintenance workers. How many possible committees are there if there has to be at least 2 housekeepers? All right, we're going to have to break this one down into cases, and in each case, we'll count the number of ways, and at the end, we'll add them up. We have to pick at least 2 housekeepers. So let's make a table of who we're going to pick to make this 4-person committee from the housekeepers, the desk clerks, not sure what's going on there, and the maintenance workers. Can't spell. Actually, I can spell very well. Okay, so let's see how many different ways he could pick from these groups. He must have at least 2 housekeepers, so let's start with 2 housekeepers. If he wants a committee of 4, he needs 2 more people. It could either be 2 desk clerks and 0 maintenance workers. Remember, he's got to have at least 2 housekeepers. 1 desk clerk and 1 maintenance worker, or no desk clerks and 2 maintenance workers. all of those have 2 housekeepers and add up to 4. But it said at least 2 housekeepers, which means there could be more. He could pick 3 housekeepers, in which case he would have to have 1 more person. So maybe 1 desk clerk or 0 maintenance workers, or 0 desk clerks and 1 maintenance worker. But if he's going to pick at least 2 housekeepers, he can pick more than 2. He can pick 2, he could pick 3, he could even pick all 4. It doesn't say he can't. But if he did that, he couldn't pick anyone else. So imposing the stipulation that there must be at least 2 housekeepers means that we have 6 ways he can make this committee. So the problem that we did before, one like this, we would have to do 6 times over, 1 for each possible combination of housekeepers, desk clerks, and maintenance workers that adds up to 4 people, but guaranteeing at least 2 housekeepers. Let's start with the first one, 2 housekeepers and 2 desk clerks. Case 1, 2 housekeepers, 2 desk clerks, 0 maintenance workers. That was the first row. Well, this is just like picking the men and the women on the committee. The resort manager has 3 decisions to make. How many housekeepers, how many desk clerks, how many maintenance workers. I know he's not picking any maintenance workers, but we're going to address it anyway. Oops, didn't mean to do that. There we go. I meant to circle 2 housekeepers. He has to pick 2 housekeepers out of how many? Out of 8. Times, he has to pick, so that was 8C2, sorry. 2 desk clerks out of how many? 3. And I didn't emphasize that the order he picks them doesn't matter, which makes it a combination. But if he's picking 2 desk clerks out of 3, then there are 3C2 ways to do that. And how many maintenance workers? None. And you might be thinking, you don't have to bring that into the discussion. And technically you would be correct, but I want to show you that you can and what would happen if you did. Out of the 5 maintenance workers, he's going to choose 0 for the committee. Let me move those C's up a little bit. That's better. I don't think we really need to have the arrows pointing downwards. All right, so let's set up each one and see what happens. I know what you're thinking. This is going to take forever, but we're not going to do all of them. We'll do a couple of them, and then I'll show you the final results. All right, for 8C2, that would be 8 factorial over 2 factorial and 6 factorial. For 3C2, that would be 3 factorial over 2 factorial times 1 factorial. Remember, the second number is the difference. And then for 5C0, it would be 5 factorial over 0 factorial, and the difference is 5. Now, if you're worried about the 0 on the bottom, remember, by definition, 0 factorial is equal to 1. All right, let's spread everything out and see what happens, or at least spread it out as much as we need to. Starting with the 8 factorial. You know what? I want to move all this stuff up some. That's better. Give me a little bit more room. All right, let's start with the first fraction. The 8 factorial on top will stop at 7 because everything after 6 will cancel. So we can just write 8 times 7 on top, and then the 2 factorial is still there. On the second one, the 3 factorial and the 2 factorial will do a lot of canceling. If we start writing 3 factorial, we could stop at the minute we start it because everything after that would be 2 times 1, which would cancel with a 2 factorial. The 1 factorial on the bottom is just 1. What does this last fraction equal? Think about it. 0 factorial is equal to 1, so for all intents and purposes, it's ignorable here. And the rest of it is 5 factorial over itself. Well, anything divided by itself is 1. This one is going to equal 1. In fact, anytime you do a combination, and the second number is 0, it's always going to equal 1 for the same reason. The 0 factorial is 1, which is ignorable. The other 2 factorials will match and cancel each other, and you just end up getting 1. All right, well, this isn't going to take too long to clean up because there's only one number in a denominator that's even worth dealing with, and that's the 2. which goes into the 8 4 times. So the only numbers that are left are the 4, the 7, and the 3. That's still 84. Equals 84. All right, so in case 1, where he picks 2 housekeepers, 2 desk clerks, and 0 maintenance workers, there are 84 possible committees to do it that way. But that was just the first of 6 possible ways to select the committee in terms of who works where. The next case is 2 housekeepers, 1 desk clerk, and 1 maintenance worker. In this case, 2 housekeepers, 1 desk clerk, and 1 maintenance worker, we pretty much do the exact same thing we did before. We just have to be careful in the setup. If he's choosing 2 housekeepers out of 8, then that would be 8C2. If he's choosing 1 desk clerk out of 3, that would be 3C1. And if he's choosing 1 maintenance worker out of 5, that would be 5C1. Let's see what these set up to be. Well, this one's the same as it was before, so I know what that's going to do. It's 8 factorial over 2 factorial, 6 factorial. The 3C1 will have a 3 factorial on top, a 1 factorial on the bottom, and the difference 2 factorial on the bottom. 5C1 will have 5 factorial on top, 1 factorial on the bottom, and the difference 4 factorial. The setup and cancellation will work exactly the same way for this one. 8 factorial, we can stop writing at 7 because everything from 6 down to 1 will cancel with the 6 factorial. The 2 factorial, however, remains and gives us 2 times 1. On the second one, the 3 factorial can start and stop at 3 because everything after that will cancel with the 2 factorial, and there will be a 1 factorial left on the bottom. And in the last one, the 5 factorial will start at 5, but we can stop it there because everything 4 down will cancel with the 4 factorial, leaving just the 1 factorial. Well, this one's not too bad either. This 2 will go into that 8 4 times, and let's see what's left over. 4, 7, 3, and 5. With a calculator, it wouldn't be that hard to figure out what that equals. Let's see, I'm going to do it at a different order. 5 times 2 is 20. 7 times 3 is 21. 21 times 20 will end in 0. 21 times 2 is 42. Insert your own joke there. So if he picks 2 housekeepers, 1 desk clerk, and 1 maintenance worker, then there would be 420 ways he can make a committee in that case. Remember, in case 1, where he picked 2 housekeepers, 2 desk clerks, and 0 maintenance workers, there were a total of 84 committees. We've done these 2 rows. We haven't done these last 4. I'm not going to do them all individually, but I will summarize them for you in this last page. In this table, you see all the combinations of housekeepers, desk clerks, and maintenance workers that add up to a committee of 4 under the condition that there are at least 2 housekeepers. I also have a column for the setup to count the total number of ways to select such a committee and the actual number of committees in the last column. We've already calculated the first 2 rows. 2 housekeepers out of 8, 2 clerks out of 3, 0 maintenance workers out of 5. Let me highlight the row as I'm reading it. We've already completed the first row. 2 housekeepers out of 8, 2 clerks out of 3, 0 maintenance workers out of 5. The setup was 8C2 times 3C2 times 5C0, and that was a total of 84 committees. We also did the second row where we had 2 housekeepers out of 8, 1 clerk out of 3, 1 maintenance worker out of 5. The setup was 8C2 times 3C1 times 5C1 for a total of 420 different committees. We're not going to calculate all of these. I'll just show you the setups and the final answers. For the third row, 2 housekeepers, no desk clerks, and 2 maintenance workers, it's 8C2 times 3C0 times 5C2, or Of 8 house workers, choose 2. Of 3 desk clerks, choose 0. Of 5 maintenance workers, choose 2. And if you work that out, that equals 280. For the third row, the fourth row, of 3 housekeepers, 1 desk clerk, and no maintenance workers. Out of the 8 housekeepers, we choose 3. Times, out of the 3 desk clerks, we choose 1. Times, out of the 5 maintenance workers, we choose 0. That ends up equaling 168. In the fifth row, 301. Of the 8 housekeepers, we choose 3. Times, of the 3 desk clerks, we choose 0. Times, of the 5 maintenance workers, we choose 1. That ends up equaling 280. Interesting. I see why. I don't see why. We'll just chalk it up as coincidence. And on the last row, where we pick 4 housekeepers, no desk clerks, and no maintenance workers, of the 8 housekeepers, we choose 4. Of the 3 desk clerks, we choose 0. Of the 5 desk clerks, we choose 0. And that ends up being 70. So how many possible committees could you make? Well, you just have to add up all the numbers in the last column, and the numbers in the last column add up to 1,302. So it's a total of 1,302 possible committees. I believe I spelled that correctly. And let me just double check the math real quick, and then I'll let you in on how I got all that so fast. Yes, 1,302. So that's the end of this video, but if you want to see how I took advantage of technology, I'm going to show you real quick how I did this in Microsoft Excel. Feel free to stop the video now if you don't want to see that. All right, let's share Excel. Let me blow this up a little bit. Over here, I just typed in all the numbers, and I don't have these labeled, but these are housekeepers, keepers. These are desk clerks. I still think I spelled it wrong. Spelled that wrong. And these are maintenance workers. Let's wrap this and shrink it down. Yeah, I did misspell housekeepers. Too many Ks. All right, let's take the font size down. Again, I'm just doing some formatting issues that really aren't that important right now, but just want to show you what's going on here. We'll center those to make it easier to see. And then in each one of them, I typed how to do the combinations. For example, on this one, it was equals. The Excel command for number of combinations is COMBIN. You open parentheses, and it tells you how many are you choosing from. From the housekeepers, it was 8. How many are you choosing? This number, close parentheses, times. Combinations, open parentheses. For the desk clerks, there were 3. And then we are choosing this number in this cell, close parentheses, times. COMBIN. For the maintenance workers, there were 5. Comma, and the number we're choosing is 0, close parentheses. That calculates the combinations and multiplies them. What I did to fill in these was a simple drag and drop. For those who know Excel, if you go to the lower right corner, the white cross will become a little black cross. That means if you click and drag, it will copy the formula into the cells below, making the changes necessary when it refers to a row. And then it just calculates those. And since these are highlighted down here, it says the sum is 1,302. So there.